Hello again, AP Chemistry students. We're at section 1.5 on atomic structure and electron configuration, part 2. So it's time to start talking about the quantum mechanical model. The quantum mechanical model is going to help us sort of narrow down the more realistic view of the electronic structure. And what I mean by the electronic structure is sort of the organization and positions of the electron within the atom. Because in the Bohr model, they're kind of in those neat little rings, but the reality is a lot weirder and a lot more complex. It looks more like this. So to understand the quantum mechanical model for the atom, we need to understand all of the sort of tiers of organization. So electrons exist in what are called quantized energy levels or energy shells. And there's about 7 of these energy levels that are possibly occupied by electrons in naturally occurring elements. But there's sort of a theoretically infinite number of shells, but we'll kind of get into that in a sec. So for the quantized energy levels or shells, what we mean by quantized is that they exist at very specific energies. The electrons can only contain a specific amount of energy and exist at those specific levels. A good analogy is to think about climbing a ladder. A ladder is technically quantized because if you're trying to climb up a ladder, you need to step on the rungs. And as you climb up, you're going to put your foot on the first rung, and then to ascend, you're going to have to put your foot on the second rung, and kind of the same with your hands. And you can only ascend by being at those specific heights. If you're to put your foot or hand anywhere in between the rungs, you're not going to have anything to latch onto. So in order to climb the ladder, you need to access all of the quantized parts of it. This also is what it looks like in an atom. You can think about in that Bohr model, like the rings, those also represent the energy levels or energy shells. The electrons can only exist at those energies and nowhere in between. Now, at each of those levels, there's a further type of organization that refers to subshells and orbitals. Subshells refer to the different types of shapes that the electrons can exist in. There are different subshells at different energy levels, and there's S, P, D, and F types of subshells. And depending on the types of subshells, they're going to have a different number of orbitals that make them up. Like an S subshell has 1 orbital, a P subshell has 3 orbitals, a D subshell has 5, and an F has 7. And I'm going to go into a little bit more detail about this, but it has to do with the solutions to the Schrodinger equation. This is really complicated physics calculus equation. You don't need to know this equation at all, but what you do need to know is that this equation gives us the different solutions for the different volumes of probability space that those electrons can be contained within. So the S solutions to the Schrodinger equation are just spheres. The P's are like these, they look like they're 2 balloons tied together, sort of, and they exist along the X, Y, and Z axes as the 3 different possibilities. And then as we go to the D and the F, they get super complicated. You don't need to know too much about these shapes, but what you do need to know is that there's 1 kind of orbital for the S subshell, 3 kinds of orbital for the P subshell, 5 for the D, and 7 for the F. And when we're talking about energy levels, subshells, and orbitals, there's like sort of these 3 tiers of organization. Another analogy I can give is that it's kind of like a dresser. If you imagine the dresser as an atom, imagine the floor is the nucleus. And as we get farther away from the floor, there are different levels. So this first row of drawers, this second row of drawers, and this third row of drawers could represent the different energy levels or energy shells. And then within that level, there's different subshells. And maybe within those drawers, you open them up and there's like a jewelry box. So let's represent the electrons as like rings and jewelry. If we take those rings and jewelry and store them within a box, and then that box is stored within a drawer, and then that drawer is in a row. The row represents the energy level, the drawer represents the subshell, and the box that you put the jewelry in represents the orbital itself, where you put the electrons. Now, to go back to this complicated table here, let's first refer to our sort of legend on the side here. So there's S, P, D, and F subshells. The number of orbitals they contain are 1, 3, 5, and 7, respectively. And each orbital contains 2 electrons, or can contain a maximum of 2 electrons. So if we're looking at an S subshell, we have 1 kind of orbital for S, which means that an S subshell can hold a maximum of 2 electrons. For a p subshell, there's 3 types of orbitals, which means we can put 2 in each of them and have a maximum of 6. And then for d, there's 5, so that's a maximum of 10. For f, there's 7, that's a maximum of 14. So the number of electrons that could be stored within any one point or any one shell of the atom is going to be dependent on what subshells are available to us at that energy level. And it's not the same at every energy level. So if we look at this second part of the table on the left side, we have our shell number. So that this is corresponded to the lower numbers are closer to the nucleus. So the 1 is the first ring around the nucleus, or the first energy level around the nucleus, and then second, third, and fourth. And these are going to have different available subshells. Our first energy level only has an s subshell, which only means it has 1 orbital and a maximum of 2 electrons. In the second shell, we have both s and p subshells. So that means that we have the s, which contains 1 orbital, so that's 2 electrons, and then the p, which contains 3 orbitals, so that's another 6. So we have a maximum of 6 plus 2, and that's how we get 8 electrons for the second shell. For the third shell, now we have s, p, and d. So that means we have 5 plus 3 plus 1 available orbitals. So that means we have 10 plus 6 plus 2 max electrons. That's how we get to 18. And for the fourth shell, we have all 4 kinds. We have S, P, D, and F. So that means we have 7 plus 5 plus 3 plus 1 maximum orbitals in that energy level, and then 2 times that for the electrons. So 14 plus 10 plus 6 plus 2. That's how we get a total of 32 possible electrons in the fourth energy level. So we have 3 tiers of structure. We have energy levels that contain subshells, which contain orbitals. Let's go to here. Okay, so the periodic table is also organized in a really convenient way. I don't think Mendeleev really understood this when he was first putting the periodic table together, but there happens to be a really convenient organization of the periodic table that corresponds to the type of subshells that are available at each energy level. So the periodic table can be broken up into blocks. And these blocks kind of have a similarity of the types of elements they're in, because we have our metals here, our transition metals, and then our non-metals, our noble gases, and then our lanthanides and actinides, which technically fit in this little sliver between La and HF and AC and RF. This whole row kind of fits in between there. And there is a lot about the electronic structure of the atom that is represented on the periodic table based off of the position of those elements within it. So this highlighted part here, we call this the S block, because if you're looking at any of these elements, like any of the alkali metals or alkaline earth metals, if you're to look at its valence electrons, you know that based off of being in the S block, that its valence electrons are going to be within S subshells. Like, for example, strontium has 2 valence electrons. Strontium is here, Sr. Based off of it being in the S block, we know that those 2 valence electrons are in an S orbital or an S subshell. And anywhere on the periodic table, depending on which block it's in, the S block, the P block, the D block, or the F block, we instantly know where the highest energy electrons are within that atom. And we can always predict what the highest occupied shell or subshell is going to be. And this is also going to help us make an electron configuration, but we'll get to that in a sec. So to discuss the electronic structure, we need to figure out the electronic configuration, which is sort of an address of all of the electrons. It kind of gives us a code to tell where all of the electrons are within the different orbitals and subshells. So let's look at this diagram here. We start with lithium, the third element on the periodic table. Since it has 3 protons, we know it's going to have 3 electrons. And based off of the table we had before, since we have 3 electrons, that means we're able to put 2 in the first shell, and that's going to be in the S subshell. So that means we're going to have 2 electrons in the 1 level S subshell. And then that third electron is going to have to go into the second shell. And the first subshell that's going to be occupied at any one level is going to be the S. So that means we have 2 electrons in the first level S subshell, and then 1 electron in the second level S subshell. And the way we write that is 1s2, 2s1. What this means is that we have 2 electrons in the first level s subshell and 1 electron in the second level s subshell. Another way to show this is what's called an orbital diagram. In an orbital diagram, you have boxes. Each individual box represents an orbital, and each grouping of boxes represents a subshell. So if we think about lithium, it has electrons in its first and second shells. So here's our first shell, which is just our 1s, and then our second shell, which is the s and the p. And we have our px, our py, and our pz. Remember that the 3 different p orbitals are oriented along the x, y, and z axes. And then we're going to start to fill them up in order. S is going to fill first in the first level, and then we're going to fill S in the second level, and then we'd have to have more electrons to start filling up the P's. But if we go down the list, and as we add more and more electrons, you'll see that those electrons start to get added to those other subshells. In beryllium, since we have 4, we're going to put 2 in the first level S subshell, 2 in the second level S subshell, and then none in the P because we were able to fit 2 in there, and then we ran out of electrons. But for boron, which has 5, we're going to start to need to fill up the P subshells or the P orbitals. And you'll see that like kind of there's an order to how you fill these, and we'll talk about the rules for how that works in a sec. But the electron configuration is always going to be this code, this 1s2, 2s2, etc. And remember that the exponent represents the number of electrons, the number in front represents the energy level that we're at, and then the letter represents the subshell, the type of subshell orbital that's being occupied. So another way to show these energy level orbital diagrams with these boxes is to show them vertically. So we can add like a y-axis to it, and this y-axis is representing the energy. And you'll notice here that we start with 1s, this is our first shell, and then we have 2s and 2p. Since they both have the same number in front of them, they're associated with the same energy level. And then 3s, 3p, 3d, 4s, 4p. And you can see that these start to kind of like overlap with each other. Even though 2s and 2p are technically at the same energy level, they have a slightly different energy difference between them. And the electrons are going to start to fill sort of in energy order. So that's why the S subshell fills before the P. And it's going to always have this structure. But kind of based off of Coulomb's law, we know that the energy of those electrons, like the force acting on those electrons, and therefore the energy that they need to have to occupy that space, is going to they're going to need to have more and more energy to get farther away from the nucleus to have that like weaker force acting upon them. It's kind of like if you're standing on the Earth, there's a really strong gravity holding you to it, but the further you get away from the Earth, the less that gravity is affecting you. But with the energy levels, there's kind of this confusing thing that happens where the further you get out, the like kind of closer and closer they get away from each other because it's like leveling off exponentially, which means that they start to like overlap with each other in weird ways. You see, here's our first shell 1s, here's our second shell 2s, and then our third shell, the 3d starts to sort of overlap with the 4s and the 4p in terms of energy levels. But this kind of maps to the periodic table in a way, and we'll get to that in a sec. So I kind of already talked about this slide in terms of what the electron configuration looks like. So just review that in a sec. All right, so what I was just talking about in terms of the electrons filling certain subshells in a specific order, this is called the Aufbau Principle. When we're building up the electron configuration, when we're sort of deciding what electrons go into what subshells, we need to follow a certain order. And the Aufbau Principle says that the electrons are going to go into the lower energy level orbitals first. And remember that the lower level energy shells are the ones that are closest to the nucleus. So we're going to start with our 1s level. Then we're going to go to our 2p, 2s and 2p level, and then we're going to go to 3, etc. But the order in which they go in is kind of based off of that weird overlapping effect where sometimes we fill the S before we fill like the D and the P. And kind of a diagram that's often shown is this one with the arrows. If you like line up 1s, 2s, 2p, 3s, 3p, 3d, and then draw backwards diagonal arrows kind of through the rows like this, it actually shows you the order in which they fill. So we go from 1s to 2s to 2p to 3s to 3p to 4s. etc. And I know this could be kind of confusing, but a good way to remember how to do this is to think about the periodic table. Now, this might be a little bit confusing, but the one thing that you have to remember here is I kind of explained the blocks before. So these green ones are the S block, these blue ones are the P block, these pink ones are the D block, and these yellow ones are the F block. And remember, the block represents the last electron that you would put in the atom is going to be in that type of subshell. And if we look at the side here, for the S and the P subshells, the energy level that's associated with the electron that will go, the last electron that'll be added to that atom, is actually, it kind of maps nicely to the energy levels. So if like we have 1s, 2s, 3s, 4s, 5s, 6s, 7s, kind of in order, like cesium, its final electron is going to be in a 6s subshell based off the fact that it's in the 6th row. Same for the P's. For like neon, its last electron is going to be in the 2p subshell and is in the 2nd row. For xenon, it's going to be in the 5p because it's in the 5th row. However, these energy levels don't map so nicely to the rows when we're looking at D and F subshells. And that's because they start to overlap, kind of like we saw in this diagram. The 3D energy level, even though it's in the 3rd energy shell, technically has an energy slightly higher than the 4s subshell. So they're going to fill in a weird order. It's going to go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. It kind of goes out of order. So a way to remember this weird order is one to either understand this diagram or understand how it maps to the periodic table. Because when we look at the periodic table, we have this little diagram here, this 3D, 4D, 5D, 6D. What that's telling us is that even though we're in the 4th row before we start to get to one of these D subshells, these D subshells are technically in the 3rd energy level. So the 4s1 and 4s2 corresponding to potassium and calcium, that 4th S subshell is going to fill before the 3D subshell. So just remember that the D block here is going to be 1 energy level less than the corresponding S subshells for that level. So if we're talking about the element scandium, the electron configuration is going to end in 4s2 and then 3d1. All of our D subshells in that row are going to be 1 energy level less than the S's that came before it. But if you read the periodic table left to right, it's always going to correspond to the electron configuration. We're always going to start 1s, and then 2s, and then 2p, and then 3s, and then 3p, and then 4s, and then 3d, and then 4p, 5s, 4d, 5p, and then 6s. And then where this gets really weird is that the F block, the F energy levels, are actually 2 energy levels less. So once we get to like lanthanum, we're going to have 1 electron in the 3D, but then once we get over to the lanthanides, these are going to be 4F. So if we're to like look at something like cerium here, it's going to be 6s2, 5d1, 4f1. And I know that can be a little bit confusing, but as long as you read the periodic table left to right and remember that the D block ones are 1 energy level less and the F block ones are 2 energy levels less, you'll be able to remember what order to put them in. And this video is already getting a little bit long. We're at 19 minutes now. So I'm going to pause here. I promise in the following slides, we're going to do a lot more examples of this with the more complex ones sort of towards the bottom of the periodic table. So I'll see you there.